Hello everyone. In the previous class, we discussed about the types of the toppling failure, and I mentioned to you that in which type of rocks a particular type of toppling failure is going to occur. So today we will start the analysis of the rock slopes experiencing toppling failure mode. Before we go ahead with the limit equilibrium analysis, first let us try to understand the kinematic analysis of the rock slope undergoing toppling type of failure. So, the potential of toppling is being assessed from the two kinematic tests. These tests examine first the shape of the block and second the relationship between dip of the planes forming the slabs and the face angle. If you recall, we had discussed these kinematic analysis for the plane as well as the wedge failure when we were discussing about the graphical representation of the geological data and its application. At that time, we did not discuss the kinematics of the block toppling failure. So, in this case, there are two things which are to be tested. The first one is the shape of the block and the second one is the relationship between the dip of the planes forming the slab and the face angle. It is emphasized that these two tests are useful for identifying the potential toppling conditions, but these should not be used alone as the method of stability analysis. We need to be careful about it. First, coming to the block shape test. So, you see here a figure. This figure gives us the conditions which are differentiating between stable, sliding or the toppling blocks with the height of the block as y and width as delta x on a plane which is dipping at an angle of psi p. The friction angle between the base of the block plane here is phi p. So, block is going to be stable against sliding when psi p is less than phi p. That I am marking as equation number 1. This block will topple when the CG of the block lies outside the base. As you can see in this figure, it has been shown that this is what is the CG, and if I just drop here, see this is lying outside this base area. And this condition would be satisfied when delta x upon y will be less than tan of psi p, and I mark this equation as equation number 2. There is going to be the second test. Once the block test has been conducted, then this interlayer slip test is conducted. This is the requirement for the toppling to occur, that the shear displacement on the face to face contacts on the top and bottom faces of the blocks. First is that the sliding on these faces will occur if the following conditions are met. What are those conditions? The first condition is the state of stress close to the slope face is uniaxial with the direction of the normal stress sigma aligned parallel to the slope face. Take a look at this figure. Here the state of stress near this slope face is uniaxial, and this direction of the normal stress, which is sigma, here has been shown. This is parallel to the slope face. That means this is parallel to this slope face. Now, sliding on these faces will occur if the earlier condition is met, along with this particular condition also, that when the layers slip past each other, sigma must be inclined at an angle phi d with the normal to the layers. So, this is what are the layers. Where these phi d is the friction angle of the sides of the blocks, that is friction angle here. If psi f is the dip of the slope face as has been shown in this figure, this is what is your psi f, and psi d is the dip of the plane forming the sides of the block. So, you have seen that there were blocks. So, this is what is the side of the block, and this angle is psi d. Then the condition for the interlayer slip is given by these equations 3 and 4, that is 180 minus psi d should be greater than or equal to 90 minus phi d, or if you just shift the terms here and there, and then this same relationship can be written as in this particular fashion, that is psi d must be greater than 90 minus psi f plus phi d. So, the equation 4, if this is satisfied, we would say that the interlayer slip will occur. The other kinematic condition for toppling includes that the plane forming the blocks should strike approximately parallel to the slope face, so that each layer is free to topple with little constraint from the adjacent layers. The observations of the topples in the field is used to identify whether the instability is possible or not, and this instability will be possible when the dip direction of the planes forming sides of the blocks, which is represented by alpha d, is within about 10 degrees of the dip direction of the slope face, which is given by alpha f. You remember we represent the dip by psi and dip direction by alpha. So, the same convention of the notation we are following here. So, this condition can be written in the mathematical expression form by this equation number 5, that mod of alpha f minus alpha d must be less than this 10 degree. Now, these conditions 4 and 5, which I have again written here in this slide, these define the kinematic stability of the topples, and this has also been shown in this stereo net. So, the toppling would be possible for the planes for which the poles lie within the shaded area, that is this shaded portion. So, you know that the planes can either be represented by great circles or the poles. So, we have different planes along which the toppling may or may not occur. So, we have to test whether the toppling will occur or not. So, if we draw the pole of those planes on this stereo net, and if that pole falls within this shaded area, then the toppling would be possible for such planes. Plus, The additional conditions which we already have defined with respect to equation number 1 and equation number 2, that should be satisfied as far as the shape of the block is concerned. So, this condition plus the conditions given by equation number 1 and 2, all these should be satisfied for the toppling to occur along any plane. Coming to the limit equilibrium analysis of toppling on a stepped base, we are going to consider some simple cases in order to provide you the basic understanding of the factors which are important in the toppling failure and also in allowing the stabilization options. Because if the factor of safety works out to be less than 1, then we need to adopt some stabilization measure for the slope stability. The stability analysis in case of the toppling failure involves an iterative process in which the dimensions of all the blocks and forces which are acting on each of them, they are calculated. Then the stability of each block is examined, and this sequence is done from the uppermost block, and then we come towards the toe of the slope. Now, this each block can either be stable, it can topple, or it can slide, and the overall slope would be considered unstable if the lowermost block is either sliding or it is toppling. So, we need to be careful about it that in case if the lowermost block is either sliding or toppling, the overall slope is to be considered as unstable. The basic requirement is going to be the friction angle on the base of each block should be greater than the dip angle of the base, so that sliding on the base plane does not occur in the absence of any external force which is acting on the block. And how this condition can be ascertained mathematically by using equation number 1, which I have already discussed with you. Keep in mind that we are talking about the toppling failure. The limit equilibrium method of analysis is ideally suited to incorporate external forces which are acting on the slope to simulate wide variety of actual conditions that may exist in the field. We may not be able to take up all those actual cases here in the class, but this limit equilibrium method is capable of considering all those factors. What we are going to discuss is a simple case in order to make you understand that what exactly is the basics behind this toppling failure of the rock slopes. Now, if the lower blocks or the lowermost block is unstable, then tensioned anchors with a specified tensile strength and plunge can be installed in these blocks in order to prevent its movement. So, this is a kind of a stabilization measure which can be adopted. In case of the ground motion due to earthquake, that also can be simulated by a pseudostatic force acting on each block. Then water forces can also act on the base and the side of the each block, and the load which are produced by bridge foundations can also be added to any specified blocks. So, in this particular manner, this limit equilibrium method of analysis can take care of many such external factors which are more relevant in the field. But we will first learn about the basics behind this limit equilibrium method of analysis in case of the slopes experiencing toppling kind of failure. So, coming to first the block geometry, you can see here that there is a figure which is having the slope face and these columns are there and the toppling failure has been shown here. There are three types of blocks which have been shown. First one is stable. So, this is like with the inclined hashed portion. So, this and this block they are stable. Then these three blocks which are next to these stable blocks, they have the tendency to topple, and the blocks which are even below these blocks which are undergoing or experiencing the toppling, they will slide and has been represented by the hatching in this particular manner. So, there can be three types of blocks: stable, the block which is toppling, the block which is sliding. So, we need to find out the block geometry. That is the first thing which we need to do as far as the limit equilibrium analysis is concerned. So, in case of the block geometry, the first step is going to be that we need to calculate the dimensions of each block. Now, the assumption which is made here is that all these blocks are the rectangular blocks having width delta x and the height yn. So, if I take the nth block which is here, so the height of this block, that is from its base to its top, that is what is yn. So, if it is first block, its height is going to be y1, y2, y3 and so on up to yn. Now, the dip of the base of the block is given as psi p, which you can see that it has been shown like this here. This angle is psi p, and the dip of the orthogonal planes which are forming the faces of the block, that means these planes, this has been considered as psi d, which is this angle. And there is a relationship between psi d and psi p, which is given as psi d is equal to 90 degree minus the psi p. The slope height is represented by capital H, which has been shown here. The face is excavated at an angle of psi f, while the upper slope above the crest is at an angle of psi s. So, you see that it is something like this. So, this is psi f and this portion here is psi s. The angle of the base plane is represented by psi b. You can see here in this figure that the base of these toppling blocks is a stepped surface. You can follow the way I am drawing and you can see that this is a stepped surface with an overall dip of psi b. You need to take a note that no explicit means are available to determine this psi b, but since it is necessary to use an appropriate value for psi b in the analysis as it has significant effect on the stability of slope. So, we take the average value of psi b. How to choose this, we will see it little later. Now, once we need to know the block geometry, So, for that first we need to know that how many number of blocks are going to be there in that geometry. So, let us try to obtain those number of blocks. The assumption here which has been made is that the dimension b which you have seen in the previous slide is going to be same for all the blocks. So, I am going to draw a simple figure in order to derive that how you can obtain these number of blocks. So, you see here that we have the simple figure. Say this is the lower portion of the slope and this is what is the upper portion of the slope. And this is the failure surface. Now, this is what is your base, that is psi b, although it is stepped, but here I need to take the average angle. So, that is what that I am considering. This angle here is psi f and this angle at the upper portion is psi s. Now, I mark this point as point A, this as point B, this is C, this point is D here and so basically it is this line. So, this point here is the point E and this is your height h. Now, just imagine that if your psi s is equal to 0, if this would have been equal to 0, that means that the slope would have been this face and then this horizontal line. Then in this case, the number of blocks would have been h cosec psi p divided by delta x, and I am assuming that for each blocks this delta x is going to be same, because you see that this distance would have been h cosec psi p and delta x was the dimension along this basal plane. So, if I divide that by the delta x, this whole distance, I am going to get the number of blocks. But in this case here psi s is not equal to 0, it has some value. So, what we are going to get is AC will be equal to EC minus EA, and this is going to be H cot of psi b minus H cot psi f. Now, you consider the triangle ADC, that means this triangle ADC, this triangle. What we will get is AC, this AC, and in front of this side this is the angle. So, this angle, what this angle would be, you see here this angle is going to be psi b minus psi s, because this total angle will be psi b and that is how that you will get here. This angle is psi s and you will get psi b minus psi s. So, this is going to be, I apply the sine rule, sine psi b minus psi s, that is going to be equal to C d So, this is what is your CD, and in front of this you have this angle. So, this is going to be sine of psi s. So, from here I can get CD is equal to AC sine psi s divided by sine psi b minus psi s. Now, AC we have obtained here. So, just substitute it here. What you will get is H cot psi b minus cot psi f, and there will be a bracket into sine of psi s divided by sine of psi b minus psi s. This is what that we are going to get. So, let us see how can we get the number of blocks in this case. This is going to be equal to BC plus CD divided by delta x, and therefore, this n is going to be h upon delta x. BC we saw it is h cosec psi b. So, this will be cosec psi b plus cot psi b minus cot psi f multiplied by sine of psi s divided by sine psi b minus psi s, and this is what I will write here as equation number 6. Now, this is what is going to be an ideal system, because we considered that all the blocks have same delta x and same b. But what happens in the field? You will have different b and other parameters. So, we have to be careful about it. Now, this psi b can be taken approximately as psi p plus 10 degree to psi p plus 30 degree. I am marking this equation as equation number 7. So, this is how one can consider, as far as the ideal system is concerned, the number of blocks. But in case of the field situation, different conditions can be there and which also can be accounted for. But for the time being, we are restricting ourselves to this simple case only. Now, when we go for the numbering of the blocks, these are numbered from toe upwards. That means the block, bottommost block at the toe will be numbered as 1, then go upward 2, 3 and so on. Say this is the nth block and this will be your n plus 1 and so on, say m number of blocks are there. So, lowest block I will write as block 1, and the upper block for which the analysis is being carried out is going to be block n. So, here height of nth block below the crest of the slope. Now, that is going to be yn as n into a1 minus b. This is equation number 8. See, here you need to keep in mind that I am considering this b same for all the blocks. Otherwise, I will not be able to arrive at this expression. This highest block can be below the crest, or it can be at the crest, or it can be above the crest. So, in case if it is above the crest, what will happen? I will have yn as yn minus 1 minus a2 minus b. This will be equation number 9. See here, this is what is the a2 dimension, where this a1, a2 and b, they can be determined in terms of delta x and these dip angles. How? See, a1 will be written as delta x tan of psi f minus psi p. I will make it as equation number 10. Then a2 will be equal to delta x tan of psi p minus psi s, that is equation number 11, and b is going to be equal to delta x into tan of psi b minus psi p. This is equation number 12. So, this is how the block geometry for each of the block can be determined. Now, the second step is going to be the block stability. So, there are 3 groups according to the mode of behavior. I already explained this to you that there can be stable blocks, there can be toppling blocks and there can be sliding blocks. So, the first set comprises of the stable blocks, and this will be in the upper part of the slope. As you can see, this block and this block, they are the stable blocks. In this case, the friction angle of the base of the block is greater than the dip of this plane. That means phi p is more than psi p, and the height is limited such that the center of gravity of these blocks, it lies inside the base. That means that this condition is satisfied, that is y upon delta x is less than cot of psi p. The second set has the intermediate set of the toppling blocks as given by these 3 blocks in this particular figure, and in this case the CG lies outside the base. That means that these blocks will topple. And the third set of block, which is in the toe region, these are pushed by these toppling blocks. So, let us say that these 3 blocks are the toppling blocks in this figure. So, these will push these 2 blocks which are lying in the toe region, and therefore, these will experience the sliding. Depending upon the slope and the block geometries, the toe blocks may be stable, they may topple or they may slide. So, this was all about the block stability, how the mathematical expression for this limit equilibrium analysis of the rock slopes undergoing toppling type of failure mode is carried out, that we will take up in the next class. Thank you very much.